cloud. Perfect. So Amir will introduce you. Thanks, Amir, and everybody. I'll give the word to Amir now.
Okay, great. So thank you, everyone. Hopefully we are going to start, and hopefully we have more people coming, but I think that's the time to start. So this is the first session of the webinar of Youg ISA. So we had it last year, and we are going to continue this year as well. So hopefully every month we are going to have one session, and we are going to communicate this later. But this is the first session, and we are delighted to have Larry Lacey, Dr. Larry Lacey from Director of the Lacey Solutions here, talking about the topic of characterization of the probability and informative entropy of a process. And there is actually two papers that Larry is going to focus just for the talk today. So he has a PhD in applied statistics from UCD, and more recently, MBA from the Warwick Business School. So Larry, that's floor is yours, and thank you so much. You can start whenever you're ready.
Yeah, thank you, everybody. I regard it as a great opportunity to present some work I've been doing of late. So yeah, as Amir said, I did my PhD many moons ago, applying the theory, optimal design theory to exponential processes. So in some respects, as you'll see, there's oblique relation with the work I'm doing that I'll be presenting today. Okay, so you see the title of the presentation. So a key word here is process. So I'm going to be talking about processes, okay? But these processes I'm going to be focusing on expansionary processes. And they could be contractionary ones, but I'm not talking about them for this particular presentation. It's on expansionary processes. And the applications I'm going to share with you today are in relation to economics. And two aspects of economics in particular, the broad money supply and hyperinflation. Rightio, so as Amir mentioned, this is effectively a summary of two recent papers that you can refer to at your leisure for further detail. Okay. I should point out that these are two in a series. So at the moment there's 4 in the series. Hopefully there will be more in due course. But these are the first two that are focusing on theory stroke methodology. Okay. So the structure of my presentation is a little bit of introduction, then a little bit about theory, then applications, the ones I've mentioned, the economic applications, and then potential future applications. So you'll see that the way the presentation is structured, that there's natural breakpoints whereby people can ask any questions you may have. So I'd ask you to keep your questions on hold until we get to a natural breakpoint, okay? So as I mentioned, I've had the interest in exponential functions over the years. And indeed, a lot of work I've done has involved log transformations of data for various reasons, including, transforming a variable that's log normally distributed into one that's ordinarily normally distributed. There's similarities I've done in terms of work I'm going to be doing. Okay, so here is the process I'm going to be considering. Okay, so as I said, the key word here is process. So let's assume to begin with, i.e. the initial state, we have a random variable with a determined outcome, i.e. it's got a probability of 1. Okay, so that's the initial state, okay? And let's assume that in this initial state, the sampling space is 1, okay? So it's a determined outcome, probability 1. But let's also assume that this sampling space can increase can increase. And let's assume there's a uniform distribution over this discrete sampling space. Okay, so the question is, well, what's going to happen to the probability as the sampling space increases? And then a related question is, what happens to the information entropy of the process? Okay, I want to look at it in a few different situations. The first one is going to be maybe a simple exponential expansion of the sample space. And then I'm going to talk about sampling space expansions by means of different functional forms. Is that kind of clear? But in case that's not kind of clear, here's the main points. So we're talking about a sample space that can expand, okay? We're talking about a uniform distribution. And to make life very simple, we're assuming that the sample space to begin with is size 1. Okay, the integer is 1, 1, size 1. Okay, that doesn't always have to be the case. Okay, so we can extend it, and that's what I've done in the references I gave you. The theory is more generalized, so you can have a sampling space of S0, where S0 can be greater than 1. And there's various statistical methodologies to convert that into to get a probability of 1, a cumulative probability of 1. Okay, but let's assume for the case of this presentation that the sample space S0 is equal to 1. Okay, and as I mentioned, we have a uniform probability distribution for the sample space. And the sample space is over the integer interval 1/s, where s is the size of the integer sample space. Okay, you with me so far? Okay, so it's always easier with these things to visualize them. Okay, so here we are, okay? So here's the initial state, okay? X0, we know it's determined, okay? There's only one sample space, so the probability is 1, okay? But the beauty of this thought experiment is that we can expand it. So let's expand the sample space. So it's currently in the initial state 1, 1, 1. So we're going to expand that. And the way we're going to do it is via doublings of the sample space, okay? You could do it in different ways, but I do it in terms of doublings. Okay, so let's do the first doubling. So what's going to happen to the sample space? It's going to go from 1, 1 to 1, 2. Okay, so the sampling interval is now 1, 2. We've gone from 1, 1 to 1, 2. Remember, it's 1s. So s is the size of the sample space, okay? So that's the first doubling. And what's happened? We're talking about a uniform distribution. So the probability goes from 1 in just one space to, we've got now 2 spaces, and the probability of being in either of them is 0.5. And so that's the blue line. Okay, so you got two points, 1 and 2. Probability is 0.1 for both. And the cumulative probability is, of course, 1. Okay, so that's the first doubling. Let's do a second doubling. Okay, the size of the sample space is now 4. Okay, we've gone from 1 to 2 to 4. Okay, Okay, 2 to the power of 2, which is 4. Okay, and the probability, as you see, has now declined to 0.25, a quarter. And of course, the cumulative probability is the same, is 1. Okay. Okay, let's do a third doubling of the sample space. We're now gone to a sampling interval of 1/8. 1, 2, 3, 4, 5, 6, 7, 8. The probability has now declined to 0.125, 1/8. As I said, this is the third doubling. So the size of the sampling space is 2 to the power of 3, which is 8. Okay. So that's the pictorial representation of the words I gave you at the outset. Okay. So, you can do this n times. So the size of the sample space after n times is going to be 2 to the power of n. The probability for any given sample space is 1/2 to the power of n. Okay. Any space within the sampling interval, yeah, is going to be 1/2 to the power of n. Okay, so that could be restructured to put it into exponential format. That would be kind of clear when we come on to the next set of slides. Okay, so I've just simply re-express the 2 to the power of n in terms of exponential log 2 times n. Same thing. Okay. So let's assume that the expansion occurs with time. It's a time-dependent expansion. Okay? And let's assume that the expansion is occurring exponentially. So the equations now become not Sn, it's now a function of time. It's a time-dependent expansion process. Okay, and for this particular process, it's exponential lambda t, where lambda is the exponential rate constant. Okay, and the probability is exponential minus lambda t. Okay, is that clear? You with me? Okay, so that should be, to me, that was, as I expected intuitively before I even did the maths, okay? So what about the information entropy? Okay, I'm using the Shannon measure of information entropy. Okay, the equation given. So it's just simply substituting in the equation above. And you can see that for this process, the information entropy with n, where n is the number of doublings of the sampling space, is n times log 2. Okay? But for an exponential, for a time-dependent exponential increase in the sample space, lambda t, or sorry, the information entropy with time is lambda times t. Okay? So there's the information entropy. Now, this is where it gets real neat, I think. What we can do is we can time rescale. So let t be t times the rate constant, okay? Yeah? So expressing everything in the rescale time, uppercase t, we get the expansion of the sample space equal to exponential t. We get the probability exponential minus t. And the information entropy of the process equals to t. I think that's, to me, that's beautiful. Okay. And these describe the same process. Okay, so you can describe the process in terms of the expansion, you can describe the process in terms of probability, or you can describe the process in terms of the information entropy. Okay. So that's an exponential expansion. What about an exponential decline? Again, I've shown it in detail in the paper that you can refer to at your leisure. But it's simply the reverse. You know, exponential minus t for the growth, exponential t for the probability, and the information entropy is minus t. Now, the thing about contractions is you've got limitations, statistical limitations. And of course, the probability can't be less than 1, okay? Or, which is the same thing, quite frankly, the information entropy can't be greater than or equal to 0, okay, to begin with. Do you understand me? So you can only go so far with this contraction, and they're the limitations, okay? You can express it in terms of probability or in terms of information entropy. So to me, this is kind of neat because, you know, some people think in terms of growth, some people think in terms of probability, some people think in terms of information entropy, depending on what your background is, I guess. Obviously, a statistician would tend to focus more on perhaps the probabilities, but they're kind of related very clearly. Okay, now this is where it gets kind of more interesting. Okay, so let's say we got not just a single process, but we got a series of processes. And let's assume there are simultaneous processes, okay? So it could be any number of processes, but let's assume it's 3 processes. Process 1, process 2, process 3. There are simultaneous independent processes. Okay, the key word here is independent, okay? And again, as shown very clearly in the paper, you can express the growth in the sample space, the probability, and the information entropy in terms of each of these processes, okay? So for the growth and the probability, you multiply the individual processes. And the neat thing about the information entropy is you add them. So you can see a nice property of information entropy is it kind of linearizes the issue. I like linear problems as opposed to non-linear problems. Okay. And lastly, you know, I've done a lot of work over the years on multi-exponentials. Can it be done for a multi-exponential? And sure it can. Again, I just refer you to the paper for more details. So that first paper gives the methodology, and it applies the methodology to different types of exponential processes, be they expansionary processes, be they contractionary processes, be they sequential processes, or be they multi-exponential processes. Everything you want to know about exponential processes is basically covered in the first paper. But the limitation of the first paper is it only relates to exponential processes. Okay? So as I said, it's quite a long paper because it contains a lot of detail. And as I said, the focus of that paper was primarily theoretical and methodological. So I think that's a natural break point. If you have any questions, let me try my best to answer them.
Is anybody any questions for Larry? Well, I have one. So,
sure, Raphael.
But my question would be, would you have any applications or any data that you applied this to at the moment?
Excellent, Raphael, and that's a real segue into the next part of the presentation.
Ah, very good.
Well done. You anticipated where I'm going with this.
Thanks, Amit.
Okay, so any real world examples? Well, do you have any ideas? An expansionary process. Contractionary process. Okay, it was just in case people might have had some ideas. No big deal. Oops. Okay, I'm going to use the broad money supply. Like the broad money supply is kind of in the news. And I'm particularly going to look at the US broad money supply, is because the US dollar is the central reserve currency of the world. So if you know about the US broad money supply, you probably know about the broad money supply of the world. And the reason money supply is kind of in the news is because, well, where does money come from? Does it come from a money tree? No, it comes from a computer. Okay. So what we have here is effectively the money supply, the US dollar money supply from the year, so it's a time series, okay? It's from the year 2001 to 2019. Okay, so I'm putting T0 as 2001, okay? So you'll see in the graph, it goes from 0 to 18. That's 2001, 2009, okay? So this is the annual money supply, okay? So that's what the blue dots are. And you can see it increases with time, as you'd expect. Or maybe you wouldn't expect it. Maybe you say, well, why isn't it constant? Well, there's a good reason, I think, economically why it's not constant. Probably wouldn't be such a good idea for it to be constant, but I'll come on to that later. But you can see it increases. Now, I purposely chose 2001 to 2019 for the simple reason, and in the middle of that time series, you may recall back in 2007-8, we had a slight problem where the banking system went into cardiac arrest. Okay, so that's why I chose it, because it's not your typical 20-year period. It had a major economic dislocation in the middle of it. And you can kind of see it from the money supply. You can see something weird has happened in 7-8. See what I mean? It kind of goes quite different to trend. Okay. Okay, that's the first point. So that's the money supply. My internet connection is unstable. Hopefully it'll remain stable. Okay, so what you'll see in the dotted line is I've put a mono-exponential fit to it. Okay, and you can see the coefficient of determination is about 98%. So it's a pretty good, reasonable fit. Okay. So, you know, I put it to you, notwithstanding this major dislocation to the world economy, there's approximately an exponential increase in the money supply over that time period. And the key number there is 0.555. That is the rate constant. And the other number is 7.5805. Okay, so what on earth is that? Okay, that is S0. Remember I said S0 doesn't have to be 1. Here I'm setting it to 7.5 US dollars. Why can I do it like that? It's because I'm making everything relative to it, okay? The cumulative probability of 7.5805 trillion at time 0 is 1. Okay. Okay, so thinking of it as a process, what we have is we got the growth of the process, which is exponential. Okay, because it's all relative to 2001. It's exponential 0.0555 times t is. Now, what's the probability? It's the probability of that huge amount of money supply at the start, okay? That decreases 0.0555 times t with time, exponential. And the information entropy of the process is 0.055 times t. So here we have the plot of the natural log of the raw money supply, but it's the same as the information entropy. Okay, it's 0.555 times 0.0555 times t. That's the information entropy of the process. So as you can see, something weird and wonderful was happening, you know, sort of 2007, 8, 9. There are 3 years where things were going rather strangely. Okay, that's the most obvious deviation from the linear equation. Okay, so that's simply a description of treating the US broad money supply as an expansionary process. So Raphael, there's an example for you.
Thanks, Larry. That was great. Does anybody any questions for Larry at this point?
Yeah, I not a question, but I would appreciate if you can explain more. I didn't understand the intercept in the first graph that you showed. So you just explained the rate, constant rate, but the intercept that was showing, I think that the rate, the annual money supply in the first year, that's as a constant. So
absolutely.
Yeah.
So the money, yeah, absolutely. So great question, Amr. Yeah, so what we have is the intercept here. Okay, so that is the size of the money supply at the outset, at the beginning of this time series. So the time series is made relative to it. Okay?
Yeah.
So in other words, that's set to 1. So what happens in year 2, which is year 2002? Okay? It increases by a proportion. Okay, which is related, not the same as, related to the rate constant. Okay, yeah. And it grows. So yeah, if you look at the way these data will be presented in the literature, the economic literature, it would talk about the annual growth rate in the money supply. Okay,
which is the main parameter you're looking for.
Yeah, which would be sort of, you know, I don't know, 6%, something like that. Okay, so they will give you R, which is the rate. Now, the rate and the rate constant are similar, but not the same thing. But you can convert the rate constant into a rate, or a rate into a rate constant. Okay, is that clear?
Yep. Thanks.
You're welcome. Okay, so moving on. So that's exponential. So what about non-exponential expansions? So as I said, here's the, you know, this is the basic structure of the expansionary process, where it's related to n, where n is the number of doublings of the sampling space. Okay? So as I said, there's the sampling space, the size of it, there's the probability, and there's the information entropy. So what about a power function? Okay, so I looked at a couple of different examples, and this was just, the examples I chose were somewhat random, but it was more based on the maths than anything else. But I don't think the functional form really matters too much once you can determine what that functional form is. So in this case, I'm using a power expansion. So I'm saying, so we're talking about a time-dependent expansion again. I'm only interested in time-dependent stuff. Maybe expansions could happen that ain't happening in time, but I like kind of time-dependent stuff, okay? That's what I'm used to. So let's say the doublings are occurring with time. Okay, so t is equal to 2 to the power of n. Okay, So you can work out then what n is equal to. N is equal to log E2, log ET over log E2. And you can substitute into the previous equations I gave you, which are the basic equations. So this time, for a power-dependent, not an exponential, a power-dependent expansion, you get ST equals T, okay? So the expansion is directly related to time. The probability is 1 over time. And the information entropy in this occasion is log of time, okay? But that's simply T equals 2 to the power of n. But I can generalize it very easily, as I've done in paper number 2, where T is to the power of A is equal to 2 to the power of n, where A is, I don't know, greater than or equal to 0. Or greater than 0, okay? Yeah? So that's a power. So, okay, well, let's do something fancier. Okay, here I'm putting T equals to, related to, proportional to the natural log of n, where n is the number of doublings. Okay, so it's just a different functional form. So I chose that one because, you know, I just wanted to play with maths. And lo and behold, this is what I get for, again, ST, the expansion, the probability, and the information entropy. Now, the expansion is intriguing. If you look at it, it's a double exponential. It's an exponential brackets a constant times an exponential. So it's a double exponential. Okay? Double exponentials. You tend not to come across double exponentials too often, but you do come across them. And the word hyperinflation comes to mind, at least it did to me. Okay? So it's a hyperinflationary process. Okay? I think that's neat. Okay, so these are two well, not strictly speaking, non-exponentials. One is, I must admit, cheating a little bit. And I know powers and exponentials are kind of related. But you see what I mean? Like, the bottom line is, it's how you relate, you know, how you relate time to the number of doublings of the sampling space. That's the key functional relationship. And that's actually a topic of a later paper in the series, but it's not part of the topic of this presentation. Okay, so that's really kind of dealt with in, so paper 2 is really companion to paper 1. My paper 1 was too long. It was already very long. I couldn't put all this non-exponential stuff into it. So that's why I came up with a second paper, okay? And I apply it to hyperinflation because, you know, double exponential to me, it screams hyperinflation. So any questions to this stage?
Any questions for Larry?
Yeah, again, same as before, I'm looking for the application of when you have this power time dependent. So I assume that's next.
Oh, I look forward to sharing it with you. I look forward to sharing it with you. Okay, powers. Now, you see, what I've described for you guys is a process and its statistical properties. The key word is statistical properties of different types of processes. So anyway, so I've been looking at literature for you know, examples, and I came across this one. Now, so what do you see here? Okay, well, firstly, you see that for this particular process, it's an expansionary process. It's supposed to have a uniform distribution, happy days. And there are 3 processes involved, P1, P2, P3. So what's the first process? Well, it doesn't matter what it is. You know, for me, it doesn't matter. It is a power expansion. The nature, you know, the description of it doesn't matter. It is a power expansion, okay? The second simultaneous process is also a power expansion, but a slightly different type of power expansion. And the third expansion is our old friend, an exponential expansion. So what we have here are three simultaneous, independent expansions, time-dependent expansions. So do you think we have the methodology to deal with that, to investigate it, at least from a statistical perspective? I believe we have. Okay. Yeah. So that's a real world example, which I'll come back to in more detail in a minute. Okay. So I've kind of left you sort of lingering with that one, and there's a good reason for it, but because I want to emphasize from a statistical perspective, that is addressable as a statistical problem. Okay. Now, hyperinflation. So Amir, I know, like, you know, you were reading my thoughts, obviously. So, so hyperinflation has happened loads of times in terms of fiat monies over the millennia, I dare say. But the one that, you know, most of us are kind of aware of, at least in folk memory, is this Weimar Republic, i.e. Germany in the interwar years, between 1922 and 1923. So, okay, so the first question is, well, why on earth would anybody allow hyperinflation to happen? Okay. But before we get on to the why, let's look at, well, you know, what do we mean by hyperinflation? Now, the first thing I'll point out here is this, what you're seeing is a semi-log plot, okay? It's not the actual raw data. Now, what is the data? It is the value of one gold mark. So mark was the currency of Germany, okay? Still is, or well, was until the euro took over. But there was a gold mark at the time, and there was a paper mark. Okay, gold mark is made of gold. Paper mark is made out of paper. Okay, with serial numbers on it. And what we have is a time series again. This is over the period middle of 1920 to the end of November 1923. On this occasion, it's in months, not years. Okay, so time zero is, I think, June or July 1920. Okay, if you look at the plot, it's a semi-log plot, right? So for a long time, okay, things are increasing. So what does that mean? So the value of the gold mark is increasing versus the paper mark, okay? So that indicates you got inflation, okay? But the inflation is kind of under control. It's increasing, you know, relatively rapidly, but it's pretty much stable. And then in the middle, you see the point 23, it goes whoosh, okay? And then it starts increasing double exponentially, okay? Okay, so that's it. So can I describe that mathematically? Of course I can. Okay, so using the methodology I've just shown you, I can work it out. I can actually parameterize it, okay? So as I said, before t less than 23, which is July 1922, you had effectively an exponential process, a single exponential process. Okay, so approximately the inflation rate per month was about 10%. It's high, but you know, it's probably manageable. It's very, very high, like 10%. 10% per year is high, but 10% per month is pretty high. But it's probably still manageable, okay? But if you see what happens from July 1922 onwards, it just goes up double exponentially, okay? So what happens is the inflation goes up double exponentially. So it's a hyperinflationary process, which means to say that your paper money is becoming worthless. Okay, so it means that you need, wheelbarrows loads of money to buy, a newspaper, to buy paper. So that's what happens. That's what happens with hyperinflation. Things happen very, very quickly. Remember what we're talking about a matter of months. We're talking about from July 1922 until November 1923. Okay? The situation went from under control to completely out of control. Okay, so this is kind of neat because it tells you what I've described for you: price inflation and price hyperinflation. What's the difference between the two? With price inflation, you have a constant rate of increase, or approximately a constant rate of increase. Okay, that's a velocity. With hyperinflation, you've got a constant rate of acceleration. Okay, the difference between velocity and acceleration. To me, that's the difference between price inflation and price hyperinflation. Needless to say, price hyperinflation, there's only one way that can end. Okay, so that's just simply parameterized. Oh, okay. So why did it happen? Okay, like what idiot would cause hyperinflation to happen unnecessarily? So there's got to be a reason why these things happen. So of course, Germany after World War I was defeated, and there was a treaty, the Treaty of Versailles. Following the Treaty of Versailles, he had a load of war reparations to pay to the victors of the war, which was obviously France and the United Kingdom, of which we were part, by the way, at the time. So the way Germany sort of addressed paying these war reparations was effectively to print money, marks, and to use that printed money to buy foreign exchange in the foreign exchange markets. Now, of course, the foreign exchanges are not stupid. They're going to say, well, we want more of your marks with every day that passes to buy more of our exchange, foreign exchange. So inflation starts ticking up. So you saw we got to approximately 10% per month, okay? But then what happened was that methodology of being able to pay for reparations wasn't working. And the Weimar Republic was in danger of defaulting on their reparations. So what France did, and Belgium, they occupied the Ruhr, which is the industrial heartland of Germany. Okay, and that happened in January 1923. Remember, this hyperinflation kicked off in July 1922. Presumably was a desperate effort on the part of Weimar Germany to try and get the monies for the reparation payments. Okay? And then what happened was the German government said, well, we've got to protest this occupation, and did so by having effectively a general strike. But the German government paid the strikers in the Ruhr part of Germany. And the result was they're printing more and more money. That money becomes increasingly worthless. So I'm sure the Weimar Republic, the central bankers in the Weimar Republic, didn't set out on, let's create hyperinflation. I think it was a process that just happened because of events beyond their control. But once hyperinflation kicks in, that's it. That currency is doomed. And what they did was to introduce a new currency. Okay. So, any questions on hyperinflation?
Any questions for Larry? Well, maybe I'd have a question, Larry. What sort of methods would you use to maybe estimate the break point when it goes from inflation to hyper? Would you assume some sort of likelihood on the process and then try to estimate it or optimize it somehow?
As it happens, it's the subject of a manuscript number 5 that I'm hoping will be paper number 5 in the series, which addresses it from a straightforward methodology, going back to basics, going back to the sampling space. What would you need? Can you? So the way I addressed hyperinflation in paper number 2 was using this relationship between T and N. But what I did in manuscript number 5, which hopefully will become paper number 5, but it hasn't yet, is to go back to the sampling space. So what you have to do to the sampling space to create hyperinflation. So I address it. I can't really answer your question specifically now, unfortunately, Raphael, but hopefully that paper will become available at some stage and you can refer to it then.
Perfect, thanks.
Okay, so additional applications. So I've given you kind of couple of examples, and they're the 2 examples that are in the 2 papers that you have as references. But here's another one that I'm hoping to have published. And it's a hypothesis I'm evaluating. So CPI is consumer price, so it's a macroeconomic application. So CPI is the consumer price index, which is a measure of inflation. BMS is raw money supply. GDP is gross domestic product, and SAV is savings. So my hypothesis is you can explain the growth, the increase in inflation with the increase in the money supply minus the increase in the GDP minus the increase in savings. Okay, so that's my hypothesis. And if you notice, I used the words log. That was for your benefit. In the manuscript, I don't use log. I use V for velocity, which effectively is a measure of the information entropy. So this is all, you see, the beauty of information entropy to me is that you linearize nonlinear problems. Okay, so I like dealing with linear systems. They're obviously more easy to address. Okay, so that's really something for the future. It hasn't been, I can't disseminate it yet. I may never be able to disseminate it because, you know, maybe rejected or whatever. Okay, now here's one. And I'll read it out to you. Application, this is a manuscript in development. Application of information entropy, of an information entropy methodology. That's what you see, I like the information entropy stuff I'm doing. That's why I call it an information methodology. For a simultaneous independent process, named Robertson-Walker metric, also known as the FL or W metric. Anybody have any idea what the FL or W metric is? Anybody? Okay. It is the description of the expansion of the universe using the standard model of physics. I repeat, the expansion of the universe using known laws of physics. And of course, physics don't deal with information entropy. They tend to deal with thermodynamic entropy. Now, as you may know, thermodynamic entropy is kind of a special type of information entropy. Okay, so thermodynamic entropy is very, very specific. Information entropy is general. Okay, is more general than thermodynamic entropy. Okay, so that is a manuscript I'm seeking to develop. Okay, and why am I developing it? Because of this. You've seen this before. I just simply described the processes to you. But each of those processes is talking about a particular thing. So A is not, so A is a scale factor. Okay? What is the sampling space? It's a scale factor. Okay? It's an integer interval. Okay? So firstly, A and T and S and T are not too dissimilar. Okay, the first part is in relation to radiation. Okay, it's got this kind of relationship. It's proportional time to the power of a half. Okay, that is a power expansion. Okay, matter is proportional to T to the power of 2/3. And this weird and wonderful dark energy is an exponential. Okay, Hubble is that's a supposed constant. I won't go into that because it ain't a constant. It's most people, when they think of constant, assume it's fixed. And it's typically time invariant constant. It ain't a time invariant constant, but that's neither here nor there. Okay, I'll put it to you that this FL or W metric, while it is a physics metric of the expansion of the universe, it is open to statistical evaluation because it's dealing with a process that can be evaluated statistically. Any comments?
Well, I suppose I have a comment that I think it's really cool that you can apply something that is used in physics to a statistical process. That just reminds me of how you can use the Taylor power law in ecology, for example. You can approximate that and see how animals are distributed in a grid of cells, for example. That fascinates me.
Yeah, absolutely. So the bottom line is, what I'm kind of saying here, like my personal view on this is that this metric, this FL or W, can be evaluated from a purely statistical perspective to look at its statistical properties. Okay, that's all I'm saying can be done. Clearly, I'm not saying, well, statisticians can say what the laws, the physical laws of the universe are. That's clearly not what I'm saying. But what I'm saying is that this is a process. This process will have statistical properties, and this FL or W metric will have statistical properties. And why should it not be open to statisticians to look into? So, unfortunately, the FL whatever metric is kind of pretty touchy. When I say people, I'm talking about statisticians will feel pretty touchy about people dabbling in their sphere, in their discipline, dare I say it. And it's the bedrock of cosmology. So, but notwithstanding that, I'm saying that it should be amenable to statistical evaluation and interpretation. Now, obviously, for me to try and publish my manuscript on this, the chances of being successful are approximately 0. No journal will touch you with a barge pole. Okay, so I want to disseminate this, at least the thoughts, my thinking at this stage, to more widely amongst the statistical community, and hopefully to maybe make bridges between the statistical community and the astrophysical community, to see, to work in partnership to look into this. You know, I'm not saying that, we should, statisticians should just say, we own this now, we're going to do what we like with it. But we should be able to ask questions about it. Because I'm telling you, because I've looked into this, it's got peculiarities from a statistical perspective. Okay. So that's pretty much it, unless anybody's got any additional questions. And I'd encourage you to look at the two published papers, or the two papers that have been referenced for you to access, which gives you a lot more detail than I've had time today to present to you.
Has anybody any final questions for Larry? Well, I think it was nice that we were actually asking questions intertwined with the presentation, which was a really nice format. I'd just like to thank you, Larry, very much for presenting today at the webinar. I'm just going to stop the recording now. And okay, I'll just